Hello everyone. Welcome to another episode of Deep Dive Knowledge Talk. Hello everyone. Welcome to our discussion on the crucial role of execution feedback in training language models for coding accuracy. This iterative process with reinforcement learning from execution feedback, RLEF, enables models to achieve high accuracy with fewer iterations. RLEF outperforms state-of-the-art techniques and has potential applications in automating code generation, improving software development, and more. What role does execution feedback play in the training process of language models, and why is it considered advantageous for improving coding accuracy?
Execution feedback plays a crucial role in training language models, acting like a coach guiding a player during practice. When a model tries to write code and gets it wrong, execution feedback is the information that tells it where it made mistake, similar to a coach pointing out what needs improvement after each play. In the context of coding, this feedback comes from the coding environment, which checks the code and signals which parts don't work as expected. The model then takes this feedback into account, just like a player who learns from their mistakes to perform better in the next round. By using this feedback to adjust its approach, the model can refine its code over time. This method is advantageous because it allows the model to learn efficiently from its errors. Instead of just guessing, the model gets clear directions on what to fix. As a result, it can reach higher coding accuracy quickly, like an athlete who practices smartly rather than just practicing harder. This leads to better performance in coding tasks and helps the model become a state-of-the-art coder.
How does the iterative training process work with RLEF? And what impact do the 3 iterations have on the model's accuracy compared to other models that require more iterations?
The iterative training process with reinforcement learning from execution feedback, RLEF, works like a student taking a test multiple times, each time learning from their mistakes to improve. In this method, when a model generates code, it evaluates its own work using feedback from the coding environment. If it gets something wrong, it goes back, reviews what happened, and tries again, similar to how a student looks over a wrong answer to understand where they went astray. In this process, the model typically goes through 3 iterations. Each time it attempts to solve a coding problem, it gets a bit closer to the right answer, picking up valuable lessons along the way. This is particularly impactful because, with just these 3 tries, the model can achieve a high level of accuracy, reaching around 40%. In contrast, other models often require many more attempts to reach similar results. This means that RLEF is very sample efficient, like a student who can achieve high grades by studying smartly rather than just studying harder. The fewer iterations needed make RLEF models more effective and quicker in producing correct answers, which is a significant advantage in the competitive landscape of coding tasks.
What implications does the sample efficiency of RLEF have for scalability and computational resources when training coding models, especially in relation to inference scaling laws?
The sample efficiency of RLEF has significant implications for scalability and the use of computational resources when training coding models. Think of sample efficiency like a car that gets great mileage. It can travel further on less fuel. In this context, RLEF allows models to achieve high accuracy with fewer coding attempts, meaning they require less computational power to produce good results. This efficiency is essential when we consider inference scaling laws, which suggest that the more time a model spends on a task, the better its performance becomes. RLEF models can allocate this time wisely by engaging in a thoughtful step-by-step review of their previous attempts. This not only improves their accuracy, but also means that for organizations, especially large tech companies, they can accomplish more with less computational effort. In a world where companies are continually seeking to optimize their computing power, having a method like RLEF that scales well is crucial. It helps ensure that as models grow more complex, they can still be trained effectively without overwhelming resource demands. This balance between performance and resource efficiency positions RLEF as a promising method in the quest for advanced AI capabilities, making it an attractive choice for future development.
How does RLF compare to other state-of-the-art techniques in terms of overall performance and adaptability in dynamic coding environments?
RLEF stands out compared to other state-of-the-art techniques due to its impressive overall performance and adaptability in dynamic coding environments. Imagine RLEF as a master sculptor who can create stunning statues efficiently. It molds the code through focused iterations while learning from its mistakes, ensuring that each attempt is better than the last. In direct comparisons, RLEF has proven to elevate a mid-tier model like Llama 3.18b to state-of-the-art status, outperforming even more powerful models like GPT-4 that also have the chance to iterate. This showcases RLEF's ability to refine code effectively even with fewer attempts, highlighting its superior training method over traditional approaches. Additionally, RLEF's adaptability shines in dynamic coding environments where conditions can change rapidly. As it learns from execution feedback, the model can adjust its strategies on the fly, much like a skilled chef who tweaks their recipe based on available ingredients or customer preferences. This flexibility makes RLEF particularly valuable, as it can respond well to varying challenges and demands in coding tasks, ensuring high performance regardless of the scenario. All these factors combined suggest that RLEF is not just effective, but also a robust choice for training models in complex and changing environments, setting it apart from other techniques in terms of both performance and adaptability.
What potential applications do you foresee for RLEF-enhanced coding models in real-world scenarios? And how might they impact industries reliant on software development?
RLEF-enhanced coding models have several promising applications in real-world scenarios that can significantly impact industries reliant on software development. First, consider software development in general. RLEF can help automate code generation and debugging processes, allowing developers to focus on higher-level design and architecture, rather than writing and fixing code line by line. This efficiency can lead to faster product development cycles and reduced costs. Second, industries that require tailored software solutions, such as healthcare or finance, could benefit tremendously. RLEF models can generate precise code for specific applications that comply with regulatory standards. This capability ensures that critical software meets stringent requirements while minimizing human error through rapid iteration and self-correction. Additionally, RLEF can enhance educational tools for coding, providing personalized feedback to learners. By simulating a coding tutor, these models can help students learn programming languages more effectively by iterating on their code submissions and offering constructive feedback based on execution results. Moreover, industries that rely on data analysis and machine learning can utilize RLEF models to generate data processing scripts or algorithms automatically. This would allow data scientists to spend less time writing boilerplate code and more time analyzing insights and making data-driven decisions. Overall, the adaptability and performance of RLEF-enhanced coding models can lead to improved efficiency, reduced costs, and accelerated innovation across various sectors in software development, ultimately reshaping how organizations approach coding tasks.
What challenges or limitations might organizations face when integrating RLEF-enhanced models into their existing workflows and systems?
Organizations looking to integrate RLEF-enhanced models into their existing workflows may face several challenges and limitations. One major concern is the need for a well-defined reward mechanism. RLEF relies on feedback to learn, and if this feedback is suboptimal or poorly designed, the model's ability to learn effectively can be hampered. This can create hurdles in training the model to produce reliable and correct code consistently. Another challenge is the integration with current systems and processes. Organizations may have existing workflows that are deeply entrenched, and introducing a new training method like RLEF could require significant adjustments. This might involve training staff on how to effectively use and interact with the new model, which can take time and resources. Additionally, the reliance on execution feedback means that organizations need to have robust testing environments in place. If these environments are not well established or accessible, It could limit the model's effectiveness and hinder its ability to learn from its execution results. Lastly, as RLEF is a newer approach, organizations might encounter uncertainty regarding its long-term reliability and performance. There may be concerns about whether the initial successes will hold up in diverse real-world scenarios, leading to hesitance in fully adopting the technology. Overall, while RLEF holds great promise, these challenges must be carefully navigated to ensure successful integration into existing workflows and systems.
Thank you to our esteemed researcher for sharing these groundbreaking insights. As we conclude, let's recap the key takeaways. Execution feedback is essential for training language models, providing specific error correction information. Reinforcement learning from execution feedback, RLF, enables iterative training, resulting in highly accurate models with fewer iterations. RLEF is sample efficient, reducing computational resources and scaling effortlessly. It outperforms existing techniques, demonstrating adaptability in dynamic coding environments. Applications extend to code generation, software development, education, and data analysis. While integrating RLEF into workflows poses challenges, these can be overcome. We hope this discussion inspires you to explore the transformative potential of execution feedback in language model training and its applications. Thank you for attending.